Okay, so let's get started. Can everyone see the blackboard now? Okay, anyway, so it's just a single announcement anyway. So yeah, as we have discussed on Piazza, so for this assignment, you can submit via either Marcus or the GitHub Classroom, okay? So you can choose one of the two options for submitting your assignments. But I mean, if everyone picks, yeah, already seen people submitting via GitHub Classroom. So if everyone decided to pick GitHub Classroom, we might decide to just simply set up this one for the later assignments. Okay. But I mean, for this, for assignment one, like either options work. Yeah, and as I have mentioned, so lots of questions have been asked on Piazza. So it is important that you check those questions before attempting the assignment. Okay. Any questions or concerns?
Yeah, so I cloned the GitHub Classroom repo, and it looks like it's empty. Are we supposed to? Is it supposed to be empty?
Yeah, it is supposed to be empty. Yes. So
Okay.
yeah, after you have completed your assignments, you just checking all your files there. So yeah.
Okay, so we should just still follow the handout and just include
Yes.
the files that it says we should include.
Yes, that's right. Any other questions or concerns? Okay, so if no, let's go to today's materials. Okay, so in today's material, we will be continuing our discussion on introduction to LLVM. In the previous tutorial, we have discussed about the following topics. We did a review or preview on C++, and we have discussed about how to write an LLVM analyze path. On the C++, what we did is that we talk about this concept of path by reference. We talk about this notion of public inheritance, and finally, we talk about the standard template library, which, as we have mentioned, is very important reasons why people use C++. And we have also discussed about how to write an LLVM analyze path. So we start by introducing this notion of intermediate representation and optimization paths that act on those IRs. We talk about the difference between analyze versus transform paths. And we start by talking about how we could write an LLVM analyze path, which we first discussed how LLVM translates your program into LLVM modules, which is essentially a list of instructions. We discussed about how to traverse through the modulo using iterators, and how we can get more information from the iterators using downcasting. Finally, we discussed about how we could inherit from the LLVM path interfaces to implement our own paths. Does anyone have any questions about what we have discussed last week? So in today's tutorial, now that we have shown how we could write an LLVM analyze path, we'll be continuing our discussion on how could we write an LLVM transform path. And finally, we'll be discussing about how we could build up the connection between different paths. Okay. So when it comes to the transform path, the first question is, so how could we manipulate the instructions in our program? So there are many ways that we could do that. We could rely on the methods of the instruction class, the basic block class, or the basic block utility class. The basic instruction manipulations might include adding or deleting instructions from the basic blocks. I won't go into too much details on this because I think you can simply check the documentation online for how to do this properly. So, and also there's, I've written an example on how to do the basic instruction manipulation. So make sure that, you check this example after class. What we would like to talk about in more details in today's tutorial is this user-use value relationship in LLVM. So let us suppose that, we have the following code to optimize. Register 2 is equals to register 1 at 0. And register 3 is equals to register 2 multiplied by 2. Apparently, the first instruction satisfies, it is an algebraic identity, meaning that it can be optimized. So register 2 is essentially simply equals to register 1. However, what happens if we simply remove this instruction? So as you could probably imagine, because the assignment to register 2 is removed, now the operand of register 3 becomes invalid. Therefore, our program crashes because we did not update the references properly. So the question therefore becomes, how could we possibly make sure that all references, i.e. uses, are updated properly? So this is what this is why we have to rely on this the LLVM user-use value relationship. And besides, if you check the Piazza discussion board, so one of your colleagues also asked this question. So when it comes to the multiple instruction optimization in the assignment, do the two statements have to be continuous? Meaning that if let's say we have C equals to A plus, B is equals to A plus T and C is equals to B minus T, do those two statements have to be continuous? Well, they do not have to be. And in order to check for that case, you also have to rely on this user-use value relationship, right? Because there are many use cases that what you want to keep track of those use references when optimizing our program. Okay, is this clear to everyone? Okay, let's move on. So if you check the LLVM class hierarchy, you will notice that LLVM has a base class value, and it has a user class that inherits from the value. And the instruction class further inherits from the user class. What we are going to show in our later slides is that the instruction class plays the role of both as an user and as a usee in our program. So let's start by talking about the value class. The value class is the most important base class in LLVM, as most of the types that we will be using this class inherit from it. A value has a type. It might or might not have a name. And most importantly, a value keeps track of a list of users that have been using itself. And so an instruction is definitely a user. So why is an instruction a user? The reason is because the instruction keeps track of a list of values it is using. So those values are known as operands, and they are of type value. As an example here, so consider the code that we are showing now on the slides. So suppose that we have an instruction. We can traverse through its operand iterators starting from the OP begin until the OP end. And for each operand iterator, we can retrieve the value from the iterator. So this is why an instruction plays the role as an user. The reason is because so it has a list of operands that it has been using. So the question therefore becomes, so why is an instruction a use-E? So the answer therefore lies in our interpretation of an LLVM instruction. Suppose that so we have this statement, register 2 is equals to add register 1 add 0. So it is incorrect to interpret this statement as the result of instruction add register 1 0 is assigned to register 2. Instead, a correct interpretation should be, so register 2 is the value representation of the instruction register 1 add 0. So what does this imply? So this implies that, so if let's say in the later program text, we use the value register 2, what we actually mean is that so we are using the instruction add register 1 0. Is this clear to everyone?
Sorry, I don't see the difference between the two statements. Isn't the result the same as the value representation?
Well, let me see how to explain this better. Well, not really. Well, yeah, I mean, you can. I would say, so your question is, so you don't understand the difference between those two statements?
Yeah, like isn't, so the result of instruction add register 1 to 0 would be.
Well, I mean, so one way to think of this, so the first statement basically say, well, I mean, the first statement basically says that so the register 2 and the add instructions, they are two different things. So they represent two different values. Well, the second statement basically says that so the register 2 is just another form of the add instruction. Is this clear to you?
Sort of, I guess. Is it like in memory representation it's referring to?
Yeah, yes, it's that way.
Okay.
So yeah, so the former states that so the left-hand side and the right-hand side are two different things. They represent two different values. While the second statement says that so those two things, they are exactly the same. It's just like different ways of printing them. Think of it that way.
Okay.
Other questions? Is this clear to everyone? Why the instruction plays the role as an UC? So let us consider the examples that we had at the very beginning. So suppose that, again, so we have this program. So and let instruction be a reference pointing to the instruction, pointing to the first instructions that we have. So what would happen if we traverse through the operands of this instruction? So by traversing through the operands of this instruction, what we get is register 1 and constant 0, right? So what happens if we traverse through the users of this instruction? So as we can see here, traversing through the users is almost the same with traversing through the operands, except that so the operand iterator has now been replaced to the user iterator, starting from the user begin until the user end. So what would happen if we traverse through the user iterator of the first instruction? We get the second instruction, right? Because the second instruction has been using value 2, which, as we have discussed before, is just the value representation of the instruction add register 1, 0. Is this clear to everyone? So someone has a question. Okay, great. Other questions before we move on? Yeah, it is important that you understand this part because this is closely related to the second part of your assignment, programming assignment.
Hi, Bojan, I have one question.
Yes.
If we know the instruction is a binary operator, can we just, is there any way that we could directly access the operand? For example, get 1, get 2?
Yes, it's also shown in the example that I wrote.
Okay.
In the first example.
Is there any way to cast it? For example, we can cast this instruction to...
Yes, so in the example, there's also showing you how to do the casting properly. I remember in the example, I tried to cast it, show how to cast properly to a constant integer and also to a function argument. But I mean, yeah, similarly, you can also try to cast to, for instance, binary operators or et cetera, et cetera. Does this answer your question?
My question is, can we cast the instruction, not operand? I mean, cast this instruction to a binary operator instruction so we can use that.
Yes, we can.
Okay.
You just do the dynamic casting as we have described previously in the previous tutorial. Does this answer your question?
Yes.
Other questions?
Yeah, so all the users of an instruction are all instructions, right?
Not really. Well, I would say in most cases, the users of an instruction will be an instruction, but yeah, I'm not sure this is 100% guaranteed.
Okay, yeah, I was just wondering if like a basic block, for example, would be a user of an instruction.
Oh, the basic block has
possible.
a list of instructions. So yeah, I would say it's not really appropriate to say that. So our basic block is the user. Well, I mean, when you ask for the users of an instruction, usually you get the instructions that have been using that instruction. But I mean, you wouldn't get the basic block because the basic block is essentially the parent of a list of instructions.
Okay, cool. So for most use cases, instructions will be the users. Are there any like edge cases? Like in what case would there?
I couldn't think of any at this moment. Yeah. Yeah, I would say in normal cases, like the users of an instruction is just another instruction.
Okay, cool. Thanks.
Any other questions before we move on? Okay, so let's move on. So in addition to going through this, the example that I wrote in the GitHub repo, so I strongly suggest that so you also think about the following problems. So let us suppose that so we have, I think this is also a question asked on Piazza, where someone asked, so suppose that we have the program say y is equals to p plus 1, and we assign to y again using q times 2. And we have, finally, we have z is equals to y plus 3. So what do you think shall be returned as the users of the first instruction, y is equals to p plus 1? What do you think?
Z equals to y plus 3.
Is z equals to y plus 3 really using p plus 1? Well, yeah.
Yeah, because it's the value well, y is the value representation of p plus 1. And
yeah.
Y is being used in.
Well, not really. Well, check this back at home. See how this works, right? And this is also related to how LLVM translate your program.
Do we have users of this instruction? I guess there's none.
Yeah. So as I have mentioned, so is z is equals to y plus 3 really using the values that we assigned in the first statement, p plus 1? Well, the answer seems to be no. So what do you expect as the users of instruction y is equal to p plus 1? So the second question for you to think about is, so in the first half of the programming assignment, the function info path, we have asked you to count the number of explicit call sites of the functions in assignment 1. Okay, so one way to implement this is by, let's say, we traverse through all the instructions of our modulo, and for each instruction, we try to cast it to an call instruction. And if the casting is successful, we increment the counter of the corresponding function by 1, right? So this is one way of implementing it. So is there a better way of implementing it? Because that implementation has a runtime complexity that is equal to the number of instructions that we have in the program. Could we reduce the complexity to be equal to the number of functions in the program by using this user use value relationship? So the hint is that so a function also inherits from the value class. So what does this imply? As we have mentioned in our previous slide, so the value class has a list of users that have been using itself. So could you come up with a better way of counting the number of explicit call sites in the first half of the assignment in your function info path?
Can you repeat the hint again? Can you repeat the hint again?
So the hint is that so the function, an LLVM function, also inherits from the LLVM module. Also inherits from the LLVM value class. As we have described in our previous slide, the value has a list of users that are using itself, right? So what do you think could be a better implementation that has runtime complexity equal to the number of functions in your program to count the number of explicit call sites? What do you think? Anyone? Any comments? Is the question clear or is the hint clear?
Yeah, I think, would you use the value class to figure out what the users are?
Yes.
Maybe there's a function.
Yes, exactly. So yeah, because the function is also a value, so you can just directly ask for its users, and for each user, you try to pass it to a call instruction. Right. So and finally, so quite often, when implementing the optimization passes, it's quite frequently you have to update all the use references of a value at one, we have to replace all the use references of a value. If let's say we want to replace an instruction from to other values. So check the documentation for the LLVM value class and see whether you can get anything that could help you update all the use references at once. Okay, so LLVM has some functions that help you do this. Is this clear to everyone? Anyone has any questions or comments? So if there are no questions, we will be moving on to the final part of our LLVM introduction, which is on the LLVM Path Manager. Yes, exactly. So as your colleague has commented, yes. So there is a method called replace all uses with. So this method help you replace all the use references of a value with another one, which is really convenient and it's something that you would like to use in your programming assignment. Any other questions? Okay, so if there are no questions, let us continue on our discussion on the LLVM Path Manager. So remember that in our previous tutorial, we talked about this isolation between different passes. And we mentioned that the reason why such isolation exists is first, it's because we want to make our passes modular and for better readability. And the second reason is because very frequently, multiple passes might require the same piece of information. So the isolation helps us avoid redundant analysis in our program. So now that we have this isolation between different passes, how could we build up the connection between them? So the way we are going to do that is by using the LLVM Path Manager. So the first question you want to ask is, where is the LLVM Path Manager? Well, it is in the getAnalyze usage method that we inherit from the module path interface. Okay, so in the starter code for the assignment 1, we have this getAnalyze usage method, which we have already implemented for you. And its implementation is, we say, is set preserves all. So what does it mean to be set preserves all? So what does an LLVM Path Manager do? So let's see. So the first question is, what is the behavior of an LLVM Path Manager? What does it do? So the LLVM Path Manager in general has two functionality. Is to require and preserve information. So what does it mean to require information? So if let's say in path A, in an optimization path A, we require optimization path B. then by the time we run pass A, the LLVM pass manager will automatically run pass B, even if pass B has not been if pass B has not been run before, and even if we haven't explicitly required to run pass B. So what does it mean to preserve information? So if a pass A preserves pass B, so by the time A terminates, LLVM will preserve all the information regarding B, and pass B will not be rerun unless some other passes invalidate it. So to better illustrate this, let me temporarily disable sharing the screen and switch to class. So what does it mean for pass A to require pass B? If pass A requires pass B, then if, let's say later on, when executing our optimizer opt, when we specify the option A to it, the LLVM pass manager will notice that so pass B has not been run before. And it will automatically run pass B, even if we haven't specified to run pass B on our command line. So this is what it means to require. So what does it mean to preserve? If let's say both pass A and pass C require pass B, and furthermore, pass A preserves pass B, and suppose that so we run it like this opt. Suppose that we first execute part A, pass A, and then pass C. So what will happen? So LLVM will first see that so we want to run pass A, and we require pass B. So it will first run pass B, and later run pass A. By the time it runs pass C, it will see that so all the information for pass B has been preserved. So therefore, there's no reason to run pass B once again. So therefore, it will run pass C. On the other hand, however, if we do not preserve pass B, what will happen? So by the time pass C is run, LLVM will see that so the information for pass B has been validated. Therefore, I will have to run pass B again. Is this clear to everyone?
Just a quick question. When it says subsequent passes invalidated, does that mean that one of the passes modifies B in some way?
Well, not necessarily modify, but well, a better way to say is might modify. But yeah, you're right. So if let's say pass A, for instance, pass A does some mutations that invalidates the information of pass B, then I will say that so I will not be preserving your information. So this is why I don't preserve pass B.
Okay.
Any other questions? Okay, so if there are no questions, let us go back to our. Okay, so the question I have to you is, so what do you think shall be the default behavior of the LLVM path manager? So if we do not overwrite the get analyze usage method, what do you think shall be its default behavior? So apparently the default behavior for in terms of require is that so a path will require none of the other passes. But what about preserve? What do you think? So this is actually related to a very important principle of compiler optimization design. Is that so when designing our compiler optimizations, one key principle is that so it's to be conservative. So what does it mean to be conservative? So by conservative, we mean that so if let's say we have some certain assumptions, let's say we have certain assumptions about the program. So if we are not 100% that the assumptions are true, then we always assume that they are false. So what do you think shall be the default behavior in terms of preserve?
Should preserve all passes?
No. It should preserve what?
We should preserve all passes because if
No.
we're trying to be conservative.
No. So as we have discussed, in order to be conservative, what should be the default behavior? It should preserve none of the other passes. So why is that? So let us consider the examples that we have discussed previously. Okay. So if let's say pass B is not preserved, so what will happen? So if let's say pass B is not preserved, what happens is that so we rerun pass B once again, right? So I mean this is fine. I mean we just rerun another pass. We just go through another iteration of pass B is fine. So what happens if let's say pass B shall not be preserved, but we actually preserve pass B? Well, we could potentially break our program, right? Because the information that pass B gets might no longer be valid. Is this clear to everyone? So this is why, like by default, if we do not override the get analyze usage method, a path requires and preserves none of the other passes. So yeah, there is an online documentation here that has more details on the path manager. So in this course, we'll be mostly using the functions calls below. So the first one is what we have already shown in assignment 1, is set preserves all. So what set preserves all means is that so it preserves all the previous passes. So because in your function, your implementation of the function info path is an analyze path that analyzes information about your program. Because there have been no mutations, so this is why it's safe to invoke the set preserves all, to safely preserve all the information on previous of previous passes. So there have been questions. So No, so back to the previous question. Yeah. So yeah, clarifications. So the default behavior, as we have discussed, is that so a pass requires and preserves none of the other passes. Because
a question.
Yes.
Just a question about preservation. Like if we don't preserve passes, let's say, even if they're not invalidated, so like it doesn't get modified, isn't it less efficient?
I mean,
you're now running the passes more than it needs to be.
So that's a very good point, as we have mentioned. So, okay, so if let's say the default behavior is that so we preserve none of the other passes. So what do we lose? What we lose is that so we have to rerun the pass once again, right? So this is what we lose. So what happens if let's say by default we preserve the other passes? If let's say we shouldn't have done that, we shouldn't preserve it, what happens? It's possible that so the information that we get from that path might not be valid, and therefore our optimization crashes, right? So let us consider this once again. If we preserve none of the other passes, what we lose is that so we have to rerun the path, which is fine. I mean, we just have to redo the path once again, which might be efficient, but I mean, we can always get the correct result, right? The compilation might take longer, but I mean, it's fine. So what happens, let's say we preserve something that shall not be preserved? Our code crashes. So which one do you think is more serious?
Yeah, the crashing is not good, I guess.
Yeah, I mean, crashing.
Is there a way to know?
Serious?
Is there a way to know in advance if the passes have been modified?
Well, I mean, so I mean, it's up to the compiler programmer to specify that. So which passes shall be preserved and which passes shall be shall not. And here we are talking about the default behavior of the pass manager. If let's say we do not overwrite the get analyze usage method.
Okay.
Is this clear?
Yep.
Any other questions? No, by default, we mean, so what happens if you do not overwrite the method in the modular path base class? Other questions or comments? Okay, so let us continue. So we have talked about the set preserves all, that preserves all the previous passes. We talk about this. We also have another method call similar to set preserves all that tells the pass manager that we preserve the control flow graph. And we have this method called add preserved A, which add pass A to our preserved list. And we also have this add required A that requires A to run before the current pass. Okay, and get analyze A allows us to get the information that we have stored in pass A. So there is an example on this, and yeah, I strongly encourage you to go through this example after class, okay, on how pass manager works inside LLVM. So yeah, exactly. So default is always correct, and set preserves all allows you to preserve. I mean, it assumes that so we are implementing an analyze path as we have been doing in assignment 1, the first half of the assignment 1, the function info path. Then set preserves all the previous passes And yes, it's more efficient to do it because I mean those passes, there's no reason why they should not be rerun again. Any other questions, comments? Okay, so in today's tutorial, we have been discussing about how to write an LLVM transform path. And we talk about this, this notion of user-use value relationship inside LLVM. And we also talk about how we could possibly build up the connections between different passes by using the LLVM path manager, which does two major things. So the first thing is to require other passes. And the second thing is to preserve other passes. Anyone has any questions about what we have discussed today? No? Okay, so if there are no questions, again, so please submit your assignment via either Marcus or the GitHub Classroom. And yeah, also check the questions on Piazza. So there have been lots of good questions asked on the Piazza discussion forum for assignment clarifications. Okay.
I just had a question about the GitHub Classroom.
Yes. Yeah.
Where is that a separate repo or?
What do you mean by a separate repo?
Because someone had said they checked out GitHub Classroom. Is that the CSC D70 that's posted on the course webpage?
So I think the invitation.
I know you said.
Oh, sorry, go ahead.
So I have the access to Marcus for submitting the assignment, but I don't know what the other option is. Where's the GitHub?
So if you check out the, so there, I think I posted the links on Piazza on. Yeah, it's pinned. It's pinned on Piazza. It's also available on the course website. If you go to the course website assignment link, the invitation to GitHub Classroom is there. And also, if you check out the GitHub Classroom, the assignment 1 folder, the link to the GitHub Classroom invitation is also there. So let me see if I can share the screen. Okay, so if you go to, yeah, if you go to the assignments, the GitHub Classroom is here.
Yep,
the invitation is here. And if you also click on here, the link is also here. And yeah, as your colleague has commented, so the invitation link is also available, is also pinned on Piazza.
Okay, perfect, thank you.
Yeah, I mean, again, so it's up to you to submit via either Marcus or GitHub Classroom, like either approach is fine. Other questions or? Okay, so if there are no questions, I think that's all I have for today. Thank you all for coming. Yeah, again, so especially since this is Monday morning. Yeah, thanks everyone.